I like to talk a little bit about the saturation binding to measure the KD, right? So when we do TR flat assays or any like fluorescent polarization assays, you want to know the tracer binding affinity to your protein, and what you can do is you can fix the protein concentration. For example, in TR flat assays, you have a fixed protein concentration, then you scan your tracer concentration, right? So then you can get you can measure the KD between your tracer and the protein using this so-called saturation binding strategy. So here's a simulation of this saturation binding. Basically, it follows the equation like this, right? So B max is the maximum signal you can achieve with a very high concentration of the ligand, and X is the ligand concentration here. I just express this X as the KD. For example, when your ligand concentration, or say here tracer concentration, equals to KD, that's when you achieve half maximal of your signal, right? So essentially you have 50% of your receptor bound with your ligand, 50% as free. When you have all your receptor or protein bound with your ligand or tracer, you will be able to achieve the 100% signal, right? Yeah, they will follow this equation here. So the thing is that when you have 4 KDs, right? So when your tracer concentration equals to KD times 4, you can only saturate 80% of your receptor, right? And when you have 9 KD concentration, which is here, then you can only saturate 90% of the receptor. Okay, this is very different from PK studies when you have like exponential decay, right? So after 3.3 half-lives, you decay to 90%. You decay 90%, right? So you only have 10% left. But in this situation, you need like 9 times KD to achieve 90% binding, because the equation is different. So here's the thing, right? So a lot of times you cannot use infinite high concentration of your tracer to saturate this binding. So most likely you will only be able to achieve saturation to here like 80%, or if you can get 90%, I consider as very good. But it's very hard to see plateau, right, in your titration study. So in this case, there are different ways of do the fitting. If you use Prism, actually they have they have this so-called one side specific binding, and they also have this one side total, and also there's another one side total and non-specific. I just want to briefly go through the differences of these different ways of calculation. So for the one side total binding, basically in this experiment, you do not have to measure non-specific binding directly, right? So in a TR flat assay, what is non-specific binding? Basically, that is the binding when you don't have your protein, right? So you only have your antibody against your his tag or any tag, and then you add a tracer, right? And you will be able to get a non-specific binding there. Assuming you did not measure non-specific binding, okay, this is your best solution in this case. You use this model, so-called total binding model. And in this scenario, it will calculate your non-specific binding and also will calculate your background, right? And so this portion is your specific binding portion. This portion is non-specific binding, assuming non-specific binding is linear to your ligand concentration, right? This is your background. The problem with this fitting is there are just so many parameters to be fit, right? So you need to fit background, you need to fit non-specific binding, KD and Bmax. The more parameters you have, actually the larger error bars you're gonna have, right? Because you have so many parameters to play with. So this is basically, I think, only when you don't have non-specific binding measurement, you use this one. But if you did non-specific binding experiment, like control experiment, which I highly recommend, you should not use this one. In that case, you should use this one. You should use the so-called one-side fit total and non-specific binding. This is essentially a global fitting, right? For example, this is your titration, right? So you have the total data set set as A in column A, and you put your non-specific data set as column B. And yeah, for example, for example, yeah, you put this your data in this total data in specific, I mean column A, and this so-called your control experiment in column B, and then when you do this non-specific binding, right, analyze, you do this, and analyze. So then when you choose this total and non-specific binding, if you click OK, that's the data you're gonna get, right? Um, so this is good because it will also, because they will use your background data as your background, which in this case is a specific measurement, right? So you eliminate a lot of variables from the background. So then when you do the fitting, you can get a highly confident measurement, right? So for example, here the KD is 155 nanomole, and then the 50%, 55% of likelihood is basically between 142 to 169, right? So it's only about 10 to 15 nanomole difference, right? So plus 155 plus minus 15, something like that. However, if you use just a total side binding, like what I'm doing here, this is one side total. You can see the number you get here is about 110 nanomole, right? Apparently, this is much smaller than the 155 we got when we use the both, considering both the specific non-specific. And then also, if you look at the confidence level, actually, for 95% of confidence level, you have basically 110 nanomole plus minus 30 to 40 nanomole. So your error bar is much larger, right? So this is mostly because it also has to fit your non-specific binding and background. That's why this is, although from the same data set, you can see the analysis is very different, and the data actually is different enough to propagate errors down the road. There's another way of analyzing this is basically you can just subtract all the background, right? So you can use this, you can use all the numbers and minus the average of this background, and then you can get basically baseline corrected data like here, and then you do fitting, right? So this is all the specific binding here. As you can see, if you do that, actually you get the KD about 150 nanomole, right? So pretty close to the global fit, right? Both the specific binding and non-specific binding. But this one apparently is more tedious. You have to manually subtract the background, doing all that. So you know, it's highly recommended we should do the global fitting, right, with both the specific binding and non-specific binding. Um, yes, one specific site. Yes, so this one is basically after you subtract all the non-specific binding and you only have specific binding left, and you can use this equation, right, so to do the specific binding fitting. And there's another one, this is called one side total accounting for ligand depletion. So what does it mean here, right? So this means basically, for example, if your ligand binds very tightly to your protein, right? So for example, you have 1 nanomole of your protein, and then you titrate in basically, um, 1 nanomole of your ligand, and then you already see, say, 50% of ligand bound to the protein. So in this case, your ligand, I mean, your total ligand concentration is only 1, right? So for example, 50% already bound to the protein, so you only have 0.5 nanomole of your free ligand left. But when you do when you use the previous models, you actually consider the free ligand concentration the same as the total ligand concentration. But when you have much tighter binding, that may not be true. And in that case, you have to use this equation, right, to do that. But generally, this is not a problem for most of our studies. Um, anyway, I hope this is helpful for people doing the titration studies recently. And if you have any questions, let me know.